Hello, in this lesson we will do a kinematic study of simple harmonic motion. We will see the kinematic equations that describe this type of motion, which are three: the equation of elongation, velocity, and acceleration. And we will also see a very useful tool to obtain information about the movement without mathematical complexity. It is what is called phase diagram. In the previous lesson, we saw that the simple harmonic motion is a periodic motion. It repeats over time and takes place around an equilibrium position. Then it is oscillatory. We also saw that mathematically elongation is defined as sine of omega t plus Fi. As for the velocity and acceleration, to obtain it, you know that we have to derive the elongation with respect to time. If we derive x with respect to time, we obtain the derivative of the I is a constant, and the derivative of the sine is the cosine of omega t plus phi. Remember that we then have to multiply by the derivative of the inside with respect to t, which is omega, and that's why we have that omega there. Then the velocity with respect to time is omega cosine of omega t plus Fi. If we derive the velocity again, we get the acceleration. In this case, the derivative of cosine is minus sine of omega t plus Fi. The a and omega, we had them as constants, and then we have to multiply again by the inside of the sine, which is again another omega, leaving minus the square omega sine of omega t plus Fi. If we compare the acceleration with the elongation, you can see that the acceleration is minus omega squared times the elongation. This is the kinematic definition of simple harmonic motion. If we plot elongation, velocity, and acceleration, we can compare the amplitude of these three physical quantities and also compare the phase difference between them. We can observe that the elongation, which is the one in blue, has the smallest amplitude. Then we have the velocity, whose amplitude is a omega. We can see it in its equation. It is a little larger than that of the elongation, and the largest is that of the acceleration, which has of amplitude a omega squared. We can also observe in terms of phase lags that the acceleration in green and the elongation in blue are in phase opposition. When one is maximum, the other is minimum. While the velocity is out of phase half pi with respect to the previous ones. We see that when acceleration and elongation are zero, the velocity has either a maximum or a minimum. The phase diagram will also help us to evaluate the movement and its evolution, and to obtain properties of the movement at certain characteristic points. It is a graph that relates a variable and its derivative with respect to time. But time does not appear explicitly. In our case, it is going to be a graph in which we are going to represent the acceleration as a function of velocity. For periodic motions, as in our case, the phase diagram is a closed diagram. In this particular case, it is an ellipse. Let's see how it is constructed. These will be the expressions of the velocity and acceleration of the simple harmonic motion. For simplicity, we will consider zero initial phase. We remove the cosine of omega t from the velocity expression and the sine from the acceleration expression and square them. If we add cosine squared plus sine squared, you all know it has to give 1. And we get this expression, which you can see corresponds to the equation of an ellipse with semi-axis, A and B. If we compare the equation that we have obtained with the equation of the ellipse, we can see that, in our case, what we represent on the horizontal axis, on the x-axis, is the velocity, and what we represent on the vertical axis is the acceleration. You can see it here. And that the semi-axis A in our case is the omega, which is painted in red, and the semi-axis B is a square omega, which is painted in blue. Well, let's see how the velocity vector and the acceleration vector evolve in simple harmonic motion. Let's see it in an animation. Here we see how when the spring is fully contracted or fully elongated, the velocity vector, which is the red vector, is 0. See? However, the acceleration, which I'm going to paint in blue now, is maximum. We see that when it is fully contracted, the acceleration is downward, then in the direction of the motion of the positive x's, then the acceleration is positive, while when the spring is fully elongated, we see that the blue vector is upward, in the opposite direction of the motion, then the acceleration is negative. Then, at the extremes, when it is fully contracted and fully elongated, we have 0 velocity and maximum acceleration. Let's take a look at it. Okay, which corresponds? With these points that I've marked on the ellipse. Here it's fully contracted. We see that the velocity is 0 and the acceleration is maximum and positive. Whereas when the spring is fully stretched, we're at this point on the ellipse. At this other point, where the velocity is still 0, but the acceleration is now negative. When the spring passes through the equilibrium point, either stretching or contracting, the velocity in this case is maximum and the acceleration is 0. When it is stretching, the velocity is positive, while when it is contracting, the velocity is negative. Let's check this information in the animation. We see that when it passes, I'm going to try to stop the motion when it passes through the equilibrium position. There it was lengthening. We see that the blue vector has practically disappeared. It's 0. The acceleration is 0. Because they have equalized, why is the acceleration 0? Because the resisting force is 0. Because the weight force has been equalized with the force exerted by the spring. And the velocity, which we see there painted in red, we see that it is positive. It goes in the direction of the increasing axis, increasing in the direction of the movement. However, when the spring is contracting, at this moment, again the acceleration is 0. But in this case, the velocity is painted upwards. In this case, it will be negative. Let's see it to check on the ellipse. It corresponds to these points. So that when the spring goes through a complete cycle, it will have drawn the complete ellipse clockwise. Thank you very much, that's all. Well, I leave here the kinematic equations of the simple harmonic motion, the equation of elongation, velocity and acceleration, and the phase diagram. Thank you very much for your attention.